Quantum physics and physics in general has just been a subject of intrigue to me. And whatever questions I might pose to you, from your perspective, they might be very fundamental or rudimentary, but from my side, it is something that I feel is very essential for anybody who's venturing out into this field to sort of get to know about.
Excellent. Excellent.
So, first question, somebody who's got absolutely no context about the quantum world and its workings, what is quantum mechanics?
Very generally, quantum mechanics is currently the best description of all natural phenomena that we have in physics. It started as a theory of atoms. So basically, there were many phenomena in atomic physics when people observed light that comes out of atoms. They could not account for this with Newtonian physics. It was not sufficient to explain neither the structure of atoms nor the behavior of atoms, the dynamics, the emission of light. So it started out simply because there was a need to explain experiments maybe that began 150 years ago or so. That was the origin of quantum mechanics. But then, as people started to apply quantum mechanics to everything else, the scope of the theory broadened. And at present, actually, um, it's certainly the most successful description of nature that we have. It hasn't been falsified experimentally ever, basically, in the last 100 years of its history. So initially, it was really meant to describe small phenomena, microscopic world, the world of atoms, subatomic particles, photons, the particles of light. But as I said, then it went into the mesoscopic domain, molecules, solids, explaining solids, liquids, and gases. And now we actually think that it might be a universal theory, that it could in fact apply to everything in the universe.
You know, in extension to that, as per my understanding and how far I understand the history of related to quantum mechanics, there was a time before the genesis of the conception of the idea of the wave particle duality, which sort of led towards the further development in the work towards the modern quantum things that we have now, the fundamental framework that we have now. How would you how do you see this wave particle duality and how it sort of how it's challenged in the past the intuition that we held for classical mechanics?
Yes, I think this goes right to the beginning of quantum mechanics, really, because um, initially it started with light, not with matter, and that was interesting. That Einstein realized that maybe the electromagnetic field, the field that accounts for the behavior of light, should not be perceived as classical physics perceives it, basically as a continuum, like any wave, like a water wave. It exists at all places simultaneously at all times. But Einstein thought that certain things could be explained if we think of light as being made up of small particles. And this was a really revolutionary idea. He wrote three famous papers in 1905. Um, the other two were one on relativity and the third one on the stochastic motion of Brownian particles. Actually, that's each of these papers was really groundbreaking in its own right and started a new field in physics. However, Einstein himself said that the quantum paper was the most radical. And the reason is that it challenges what at that time was perceived to be a very successful and mathematically very coherent and beautiful set of equations by Maxwell. So Maxwell wrote down the description of the electromagnetic field, the classical description, and Einstein actually was a big fan of Maxwell. So I think he found it very curious that maybe these equations are not ultimately correct, and in fact maybe light is not just a wave, but it's made up of particles, of photons. So that was the initial point in 1905. Then came de Broglie, which was the second really big step. And de Broglie simply thought that it would be funny if waves were made up of particles, but if at the same time you couldn't think of the traditional particles as being also wave-like in some sense. And that was the famous de Broglie hypothesis. He said it would look much nicer if there was a symmetry, if everything in nature had a little bit of a wave-like property as well as a particle-like property. So he postulated, for instance, that electrons should behave like waves. And this was tested very soon after his hypothesis, and it was found to be correct. If you do like a double slit experiment, with light, this is the experiment that was done a long, long time ago, and it showed what we call interference phenomenon, namely that light really goes through both of the slits at the same time when you shine light on two slits. And de Broglie said, if it's true that matter is also wave-like, then we should be able to do a similar experiment with matter. Of course, electrons being the smallest constituents were the first ones to be tested, but now we tested this with much larger objects, in fact, and they still behave exactly like waves, like de Broglie hypothesized. And that led Schrödinger, that was ultimately the birth of proper quantum mechanics, to write down the wave equation, which we call the Schrödinger equation now, which describes how matter really behaves in terms of waves. It's really a wave equation, but it's meant to hold for material objects. And then at the beginning of quantum mechanics, I want to conclude this discussion because in my view, despite what you read out there in the media, the debate is concluded, in fact. So you will hear lots of discussions. Is it a particle? Is it a wave? What kind of entity is it? Quantum mechanics does have an answer, interestingly enough. And the answer is that ultimately everything is a field. So this is called quantum field theory. Whatever object you have, you will associate a field with that. So it will start like a wave. However, it won't be a classical field. So if you think about a classical wave, you need to describe the height of the, if you're looking at a certain point, for instance, what you want to describe is the height of the wave at that point and how quickly it changes in time. So you're really describing oscillations of your wave. And if you tell me what happens at every point in space, you are basically giving me the full wave description, the full field, as a physicist would call this. The weird thing about quantum mechanics is that you cannot do this with ordinary numbers. So I can't give you a height. I can't say the height is 1 meter now, and in the next second it's going to drop down to 0.5 meter, which is how you would describe a classical wave. Quantum mechanically, and Dirac called these entities Q numbers, quantum numbers, you have to use more complicated objects. So it is a wave, quantum mechanics says, but it's not a classical wave. It's a wave whose amplitude and the phase, if you like, these are the two classical properties. Amplitude and how much does amplitude change in time, how quickly does it change in time, they become quantum numbers. And these are the numbers that obey different algebra. That was the key, and that was Heisenberg's contribution to quantum. That's how quantum mechanics started, the first proper paper on quantum mechanics. Heisenberg said you should keep the classical laws of dynamics. That's not the problem. The problem is not in Maxwell's equations. The problem is that the entities that are described in these equations are not numbers. You cannot use ordinary numbers. You have to use entities that are more general. He didn't know how to call them. They are ultimately objects called matrices in mathematics, but Heisenberg didn't know about matrices. He was too young at that time. They didn't learn matrices at the university. He called them tables of numbers. And later on, his supervisor, Max Born, realized that these objects actually are known to mathematicians. And they are called matrices. And the main property of them is that how you multiply them, the order in which you multiply them, matters. So that was the famous uncertainty that Heisenberg derived. In classical physics, if you take the position of the particle and multiply by the speed, because these are two numbers, you can invert the order and multiply them the other way and you will get the same. If your position is 5 meters away from a certain point, and if your speed is 10 meters per second, then 5 times 10 is the same as 10 times 5. Classically, there is no difference. Heisenberg found out that quantum mechanically, when you multiply position by the velocity, it's not the same as if you did it the other way around. These are these quantum numbers. They have really unusual properties algebraically. And that actually was the start of quantum mechanics. So it's a very unusual idea. His paper is extremely creative and very difficult to read, because I think Heisenberg himself was struggling with this. But the bottom line there was, the modification we have to make is that the reality is not described by ordinary numbers that we all learn in school, but it's described by these more complicated entities. And you can call them operators, you can call them matrices, you can call them Q number. There are many names that we use in physics, but they all signify the same things, that the order in which you multiply them gives you a different answer, basically. It matters.
You know, I did really like how you mentioned about Schrodinger and Heisenberg. Those were eventually points that I wanted to talk to you about, and it's really delight that you covered them.
Excellent.
I
Excellent.
I did try to think about how, okay, there are two cadres of people if we classify them: people who are either professional or studied physicists, or people who acquaint themselves with the subject and the understanding of its principles and laws and studies ongoing and of the past.
Yes.
And then there's a cadre of people which are completely disassociated with the findings or the guidelines that the theoretical subject of physics provides us with. Do you feel there's a difference in how these two
Yes.
cadres of people reflect upon and understand reality in itself? If yes, how do you sort of, um, what is your opinion about the subject of trying to bridge that?
It's a good question, actually. It's a very interesting area to explore, that the question you are raising now, because um, even within science, you could talk about people who are interested in quantum mechanics, and I think most physicists would fall into this category, because they're really interested in the nature of reality. And my feeling is that people who are not scientists necessarily, but are drawn to this, are also interested ultimately in the nature of reality. What is the world made of? What are the fundamental entities that everything is made of in this universe? What is the current kind of understanding telling us in physics? However, you could actually be very, very successful by simply applying quantum mechanics, and quantum mechanics is permeating technology more and more now. In fact, most of our engineering now in Oxford, and I think this is true in many places, is in fact becoming quantum mechanical, because you are really manipulating smaller and smaller constituents of matter. And also there is an advantage to quantum mechanics because it gives you a broader range of um, um, applications, if you like. If you are into applications, it's actually what surprised me, and it surprised me by direct experience. I was actually one of my early students was a computer scientist. So someone who is interested in applied side, in algorithms and designing programs that quantum computers could run and be more efficient than classical computers. If that's on your mind, then quantum mechanics does not require any difficult mathematics. That's the advantage. If you understand linear algebra, if you understand vectors, the point of a vector, which I think most of us learn in high school at some point, and if you've done some matrices, possibly if you're solving linear equations, some kind of Gaussian elimination, most of us again would have heard this at some point in high school. I think if you know these two, you are really well equipped to understand the foundations of quantum mechanics. You don't really need much more than that. And it was amazing for me to see how quickly my computer scientist students could get into the subject, could apply it, could come up with novel ideas, novel algorithms actually. But they were in this second group that you were describing, they were not really curious at all about what does this all mean. They were not pursuing this because they're interested in physics, in seeing whether new physics would come out, but they were simply interested in applications, either computer science, material science, engineering. Now it's going into business, into all sorts of pharmaceutical, medicine. There's a huge range of applications. And I think, like I said, I think it's very, very easy to get into that, even with very little knowledge, um, because the mathematics for quantum mechanics is not that complicated. The complexity in quantum mechanics is really more foundational. What are the key concepts? What are they telling us? Why are they so unusual? How are they different to any other physics that we learned? But if you are into applications, you are not going to be driven by these kind of questions necessarily. Um, so I suspect that's what discriminates these two groups. I've always been driven by the fundamental side. So what really interests me is whether the universe ultimately is this way, whether if we push quantum mechanics far enough, we will actually arrive at a new theory. That's really what physicists are asking. You know, we've had these two descriptions, general relativity and quantum mechanics, very successful over 100-year period plus. And the question is there another theory? Will there be a theory that's going to replace them? Make them special cases, a little bit like classical physics became within quantum mechanics. So it's really more like curiosity driven research rather than research done because of applications.
Further trying to drill you upon this matter itself, how does quantum mechanics or the quantum principles uh, contribute, or what do they tell us about the beginning of the universe?
That's a very deep question, which actually was maybe this happened in the 70s. That there was an idea which is still being explored, and I think because of the complexity of obtaining enough non-trivial experimental bits of evidence, it's in fact difficult to make a final definitive judgment on this. If you look at cosmology, then I think every few years, certainly every decade, there is almost a radical revision of ideas. But in the 70s, an idea came in that the origin of the universe is really somehow critically determined by the quantum uncertainty. So I think these are people who were thinking about quantum mechanics and general relativity, which are our two descriptions that we use completely separately. They haven't been unified yet. So that's one of the big outstanding problems in physics. And it's very natural to say maybe when the universe was small, in the early stages of the universe, both of these would have been equally important. Now, of course, if you look at large astronomical objects, they are to a very high approximation, really well described, even with Newtonian gravity. Then, of course, the corrections are required with general relativity, but all of this is classical physics. We don't really see any necessary quantum modifications at the level of astronomical objects. However, if you go back early enough, the idea was that it was even a quantum fluctuation that actually started the universe. So I think some of these key ideas, how the universe began, and in fact what propelled it to expand, are frequently argued to be quantum uncertainty and the zero point energy, as we call it. So these are the fluctuations of quantum fields that exist there even when no particles exist in these fields. Like I said, at present, these are really speculative ideas because we don't really have any evidence from our observations that this really is the case. However, it does sound to me like a good set of ideas that at least is plausible enough to give us an account of the early universe. Now, my feeling ultimately is that all of this is still tentative and that a unification of the two theories, general relativity and quantum mechanics, will probably result in a theory that supersedes both of these. So I think we will probably get to new physics, hopefully sometime soon. I think our experiments are getting closer and closer, at which point maybe we'll be able to revisit this question of the early universe. But at the moment, really, we can study one or two relevant parameters. We study what's known as the CMB, the cosmic microwave background radiation. We study the temperature of the early universe. And the second thing that we can get to are the fluctuations, the anisotropies. If you look at different directions in the sky, you may see that the temperature varies a little bit from point to point. And the question is, for instance, whether these kind of fluctuations are related to quantum mechanical behavior in the early universe. And again, we have so many theories competing to account for this, and we have no further concrete experimental evidence to really rule some of them out. So all of them are possible in a way. It sounds intuitively clear that quantum mechanics certainly played a very important role in the early stages. So I think that exists in all of these accounts, but I think it's very hard to really say more than that. And in fact, it's interesting how the competing accounts are very different as to what they say happened at the Big Bang, or whether there was even prior to the Big Bang, and whether Big Bang is just one of the many creations that are continuously happening in our universe. All of these are possibilities, but I think all of them ultimately have to take quantum mechanics into account. And maybe the ingenuity is really to try to figure out the consequences of this, and then to try to figure out accessible experiments that could really tell us how to test this. But it's much more complicated than my own field, which is in quantum optics, atomic physics, physics of small systems, where we have a fantastic control of matter. We can really, we can take an atom in the lowest energy state, and we can put it in any excited state with a precision that people say colloquially 6 nines. So it's 99.9999% efficiency. We can move electrons inside atoms, and this is a beautifully high fidelity that's required also for our technologies. Once you move away from that, if you go into complex systems, especially into the universe as a whole, then I think our uncertainty becomes much bigger and we cannot control anything. You can't experiment with the universe in the same way. You can't prepare different initial states of the universe. You just have to work with what's given to you.
From your description about this pertaining to my question, there were four key things that stuck with. First of all, before anything else, I would want you to talk about your field of expertise, quantum optics. What have been the challenges in that field, right? What are the current developments in it, and what is something that you are working towards currently, which you feel like could be a massive breakthrough in this domain?
Yes, this is like I said, at the moment there are two components of this, and both of them I think could result in breakthroughs. On the one side, it's simply a question that we believe is largely of the kind that engineers probably worry more about, which is a question of obtaining higher and higher degree of control when you couple um, ordinary constituents of matter to light. So what we are trying, for instance, to improve on, and this is a very difficult problem and extremely important for technologies in general, is to control, for instance, when we excite an atom and it emits a photon, we want to be able to control that photon. First of all, we don't want to lose the photon. We want to make sure that we grab this photon with as big a probability as it's possible. 100%, of course, is the limit there. And then on top of it, have another atom that we can get to absorb these photons. So the communication between fundamental constituents of matter that goes through the electromagnetic field, but in quantum mechanics through photons, is basically like you could think of it as a basic unit, as a basic gate of all our technologies. So I would like to be able to have an atom stationed in one place, excite it with a laser, wait for it to emit a photon, then channel this photon through an optical fiber, for instance, make sure that it goes into an optical fiber, propagates through the fiber, and then gets injected into another atom, which then gets deterministically excited. If we could do this, this would be beautiful. This would be a very beautiful unit for our quantum technologies. We're actually very far from doing that. Um, it's difficult to do this with any reasonably high fidelity. And of course, what we do then in kind of atomic physics and quantum optics is that you rely on repeating the experiment many times. So even if you fail a million times, then once or twice you will succeed in this kind of transfer. And when you succeed, you can measure the final atom and you can see that it's excited. So I think if we could improve the fidelity of this would be amazing. Now, on the fundamental side, and I think this story goes for almost um, any kind of atom that you want to take. It could even be a more complicated molecule. And of course, the state of light doesn't have to be a single photon. You want to be able to manipulate more complicated states of light that involve various superpositions of photons and so on. So that's kind of the direction in which it's going. But fundamentally, and I think that's where we are really going to have nice breakthroughs. What we really want to test with this is if we could scale it up arbitrarily. So then it goes in the direction, and I think it's beautiful here that technology and fundamental science go hand in hand. So the question technologically, whether we can have an arbitrarily large quantum computer, can we have a quantum computer made up of as many quantum bits, as many atoms as we like, is actually directly related to the physical question of do these macroscopic entities, collections of atoms, do they really behave fully quantum mechanically, or are we going to find that there is a boundary where somehow quantum mechanics either stops to apply or changes into something else, evolves into a different theory, which then becomes necessary? So to me, coupling atoms is technologically important, but what I really like to do, and that's actually where my passions come in, if you like. That's my work is all about that. Is that I'd like to apply these technologies first to living systems. So I've been doing some experiments in that direction. People call this field quantum biology, um, but I'm more interested in the quantum, if you like, than in biology. So biology is relevant to a physicist for the simple reason that there are many views on quantum mechanics which claim that quantum superpositions, this weird quantum behavior, will collapse when quantum systems encounter living systems. And this goes against my own intuition, and I'm not alone in this respect. Namely, that I think that living systems certainly are compatible. Not only are they compatible with quantum mechanics, but I think they even frequently utilize quantum mechanics to improve certain biological processes. And I think this is the field that to me sounds wide open. It's right at the beginning, if you like. And I think there are many fundamental questions that one could explore there. So my kind of the first milestone that I would like to achieve, and it's achieved in a very similar way to what I was describing. You are using a single photon, but you are mediating now not between two atoms, but between two living systems, whatever they are, whatever is simple to, usually you would think about viruses or bacteria, something that is relatively non-complex, at least biology, is still super complex for a physicist, but it's on the simple side, the simplest side as far as biology is concerned. And the first question you ask in quantum mechanics is it possible to quantum entangle? So entanglement is this famous phenomenon that Schrödinger highlighted by saying when one quantum system couples to another, then the state of the two becomes inseparable. You can no longer even talk about them as individual systems, but they become so correlated, super correlated. The word is entangled, that when you measure one of them and you obtain one outcome for a property, then the other system reflects exactly the same. And actually, we had a few Nobel prizes in physics a couple of years ago for people who have tested entanglement with very simple systems, things like two photons or two superconducting, very simple systems. What I think is interesting for us to do now is to scale this up and to try to, for instance, apply this to living systems. Can you entangle two living systems? I think this is a mind-blowing question. We don't know. It could be that we cannot. Even a negative outcome would be interesting to learn why is it that we cannot have these systems in a quantum state. And the other outstanding direction for a physicist, immediate outstanding, is gravity. So in a very similar fashion, you would like to probe whether certain degrees of freedom of the gravitational field can also behave quantum mechanically, like these quantum numbers, like matrices. So I think going into the macro domain, I see these two as burning questions, really. Gravity, is gravity quantum? If not, how do we proceed with that? Because if not, there are all sorts of issues with that view as well. If yes, then how quantum is it? And the same questions with living systems. I think we're right at the beginning, and I'm really hoping that by pushing quantum mechanics into this macro domain, we will ultimately even reach a new theory of physics. And it's great to see that the technologies are reaching this level where we can start to do these things.
Um, that's really interesting. I did not really know that you had expertise in, or you were working specifically in the domain of quantum biology and what it meant. But after you explained to me the thorough and sheer possibilities of it, it is really something that makes you think about like the true capability that this more than a century long framework of quantum mechanics actually holds.
Yes,
But again, the second thing that you talked about, gravity. And
yes,
I did try to sort of read your research paper, right? To whatever extent it could, I annotated it and everything. I might have just understood 20% of it. But anyway, the crux of it was that you do believe that gravity can or has a quantum nature and can be quantified,
yes.
right? Uh, First of all, I'd really like for you to elaborate upon that, right? And the other thing that I would like to talk to you about is, we talked about matter. You talked about how you were looking forward to you are working towards having a very good level of control over matter and how you want to enhance that. However, one thing that people who aren't associated with or aren't keen on learning about the physics and its learnings might not realize is that majority part of that actually exists in the universe is not actually matter, which is
Yes,
something like dark matter and dark energy, which is also responsible for the causation of the expanding of the universe, right?
yes.
So I'd first like you to talk about gravity and your research and the work that you are doing in that a bit more in depth. The other thing that I would like to talk to you about is, dark matter and dark energy.
Okay, great. I think great topics because again, these are the areas when you are looking for exciting research in the foundations of a subject, then these are the two things that immediately come up in physics. If you're really betting on what's going to give us the biggest amount of information, surprise, something that we didn't expect to be there, I think these are the directions to look into. Let me just explain with gravity the intuition maybe behind why I think it also must be quantum mechanical. Or if it's not, then we have to radically revisit some of the key principles that we believe in, and that's what's interesting here. So um, maybe just to go briefly back um, to the electromagnetic field, the reason why the electromagnetic field was introduced in the first place. This was Michael Faraday. Michael Faraday was possibly the greatest experimental physicist of all times. But interestingly enough, he introduced possibly the most important theoretical concept into physics as well. You can see that the two go hand in hand. And this is this idea of a field. So, why did he do that? The reason was really um, to he was guided by the following intuition, and I think most physicists are guided by this. In fact, Newton himself starts with Newton, the whole thing, who gave the law of gravity between two masses, how they attract one another. But he was very concerned that he didn't have a mechanism. It looked to him that one mass acts at a distance on another mass without anything mediating the force in between. And that was actually, to him, he didn't like that at all. He himself complained that this kind of magic should not have any place in physics. Surely things happen locally. If I do something here, I create ripples in the vicinity, and then these ripples ought to propagate. And that's actually exactly what Faraday conjectured. Faraday didn't do it for gravity; he did it for charges. He said, how do two electrons repel one another at a distance? And the answer was that the first electron perturbs the electromagnetic field, which exists everywhere in the background. So you put one electron, it creates waves in the electromagnetic field. These waves propagate at the speed of light to the other electron and then affect it. And all of our interactions in physics after Faraday are understood precisely through mediating fields. Anything, all the four fundamental forces are understood in terms of the fields that exist there that basically couple the relevant charges of these fields. And why is this now? Why is this important? Because you have if you didn't introduce the field, I want to talk about some other very bad consequences, which is, I think, I want to enlist that in support of quantum gravity. If you didn't have a field, you would have a problem also with energy conservation and momentum conservation. And these are principles we believe in very, very strongly in physics. We've never seen them violated in any context over the last 400 years. So we think they hold exactly. And the reason is very simple. As you know, think about gravity for the moment. When a planet goes around the sun, it goes at different speeds. So if it's further away, it executes an ellipse. So basically, sometimes it's further away from the sun, sometimes it's closer to the sun. When it's further away, it moves slower, its kinetic energy is smaller. So as the speed goes down, the energy of the planet, if you like, goes down as well. But the question is, now this slowing down has got to be communicated to the sun as well. So these two systems are responding to one another. Of course, the sun is much bigger and the effect is much smaller on the sun, but nevertheless, it's there always. And if you didn't have the field, it would look like magically the energy has gone down. It's not stored anywhere for about 8 minutes, because it takes 8 minutes for light to arrive from the earth to the sun. And then suddenly the sun picks up the kinetic energy by magic. That's exactly the bit that Newton didn't like. How it cannot be like that. It doesn't sound logical. And with Faraday, and of course Einstein ultimately made Newtonian gravity into a field theory. That's general relativity. With Faraday, this is not a problem at all, because when the system changes the energy, the extra deficit is picked up by the field. The field picks up the energy automatically, all done locally, and this then propagates through the rest of the universe, if you like, at the speed of light. So nothing happens magically, nothing vanishes, nothing needs to automatically jump from one place to another. So the field solves this problem beautifully. All classical so far. And now comes the quantum punchline, why I believe, if you like, that gravity ought to be quantum as well. And the same argument goes for other fields, for the electromagnetic, for the strong and weak forces. It's just that we know that these other forces are quantum. We've done the quantization theoretically, we've tested experimentally, it all works very beautifully so far. But with gravity, we've never tested this. So the logic is the following. Imagine now that two systems are coupled gravitationally, but instead of, this would be the case classically, instead of being in one location each of them is now in a superposition, in the quantum mechanical superposition of being in two places at the same time. And now this is interesting. Why? Because the field, if you put a mass in a superposition in two places, the field has to be able to respond simultaneously in both of these places. If it couldn't respond simultaneously, you automatically have a problem with conservation. It must account for the behavior in one place and the other place at the same time. Otherwise, we don't know how to treat this. All of the conservation principles have to be revised. And maybe it is like that for gravity. It's just that I think it's very unlikely that this will happen. I think gravity ought to, at least at some level, conform to this. So basically, the test would really be take two masses each in a superposition of two places. Let them couple gravitationally, and what you're testing is whether gravity couples each of these locations to each other location simultaneously. Will it act in a superposition like a genuine quantum entity, or will it only see one of these at a time, in which case it behaves classically? So it's a conceptually it's a very simple test. If you can entangle matter through gravity, you are basically showing that gravity too has quantum degrees of freedom. It does things simultaneously in different places. If you don't get that in your experiment, then, like I said, we really have to think very hard about what to do in this direction. But I think the consequences are huge because either the field picture of gravity is wrong, which can also happen, by the way. Maybe general relativity is not correct. It's not correct that it should be a field, or the field behaves in a very unusual way because um, it seems to basically violate exact conservation laws, and at best maybe it satisfies them statistically. If you repeat things many times, maybe on average energy is conserved, but in each experiment individually it could be violated. And I think this would be very difficult to understand in physics. How can this be? Of course, it can also signal another possibility, which is that there is yet another theory which sits above quantum and gravity, which accounts for this kind of behavior. But like I said, putting them together seems very difficult unless you acknowledge that both of them are phrased with exactly the same objects that have the same power, if you like. So that's kind of my motivation for that. And it's interesting that the experiment is of the very similar kind that I was describing when entangling two atoms or two molecules or two living systems. The difficulty is that gravity is a very weak force. So you would have to keep quantum superpositions for much, much longer than in these other experiments. That's the technological challenge. Can we keep these masses superposed for long enough that they could actually communicate gravitationally and become entangled in this way? So the challenge seems to be more technological at this stage, but people are getting closer and closer.
Again, very interesting. This is something that I feel that people in general should really be enthusiastic about. Because as you said, the whatever may the outcome be that there is a quantumness towards gravity or not, it nonetheless will be something that will change our perspective of how we think about the fundamental classical laws of the universe. But
Yes.
again, the other part, dark matter and dark energy.
Yes, it's a good question because actually it might well be related. And that's, I think, one of the speculations. Again, um, I will I will maybe say the same warning that I said before about cosmology and astrophysics, in the sense that I think um, the the experiments are simply much harder in these directions. We're talking about complex phenomena, and certainly we have no degree of control there. We can't do a lab-based experiment by starting with different configurations and perturbing them in different ways. But what I find fascinating, and this is again a property of gravity, and that's what you're ultimately testing with all of these things. Is this really true? In Einstein equations for gravity, all energy, anything that has energy, and in physics, everything has energy. Ultimately, it's really all about energy, the energy inside quantum fields, if you like. Anything that has energy gravitates, has a gravitational effect on other things. So you should really be thinking of one object with energy coupling gravitationally to another object with energy. That's kind of the right description there. So unlike in other fields, in other forces, where what matters is not the absolute energy, but what matters is the difference in energies. So a bit like you can assume that the energy is zero on the ground. You know, when you're looking at the ball falling down, for instance, and you're asking how long is it gonna take to fall from 10 meters down to the ground level, just simple Newtonian physics, then it doesn't matter what you assume to be the gravitational energy at the ground. All that matters is the difference between the ground and the height from which you are looking at. And it's that potential difference that governs the kinetic energy ultimately and the speed with which your ball will hit the ground. So you can attribute any energy to the ground level so long as you add the potential difference to that when you are talking about the higher level. But you might as well call it equal to zero at the ground. And this is true in all our other fields. They don't care about absolute energy. They only care about the differences between energies. The potential is exactly what drives um, all of the physics other than gravity. And that's the weird thing. Gravity sees everything, sees the 0 point energy, these vacuum fluctuations. And that is a big mystery. I think it was a mystery right from the beginning of quantum mechanics. May have been Pauli, Wolfgang Pauli, who even computed this in a very quick fashion initially, and said this sounds like it ought to have a huge effect. Actually, we surely would be able to observe this if it was like this. So that's our big mystery. Is this vacuum energy, the energy that quantum mechanics tells us exists even when nothing exists in the universe? No particles are present. We are in the lowest energy state, and yet there is an absolute value of energy that general relativity, gravity, Einstein's gravity ought to respond to. So this is a candidate, this is a beautiful candidate um, for dark energy. And like I said, some people even credit this kind of energy for the initial for the initial impetus in the Big Bang. What is it that blew up the universe? People say it's the vacuum fluctuation. Once you have a finite size, automatically blows up. There's a huge concentration of this vacuum energy in quantum mechanics, and that's what gives us the initial force for the inflation. But we don't know. And it would be interesting if that was the area. Like I said, if you do a very simple-minded calculation, it seems to me that there is too much of it almost to account for that. So the question is a portion of that responsible? Should we be calculating it differently? So there's a big mystery there. Why is the number so big? Some people call this the most embarrassing mistake or prediction of quantum mechanics. It gives you a huge number of energy, 0 point energy in the universe, and we don't seem to see any manifestations, any effects of that. However, that's exactly what dark energy could be. Dark matter is potentially a different topic. Although it could be related, we don't know. It's wide open. But dark matter signals more that there are possibly even extra particles that we haven't detected even, which could contribute gravitationally, but otherwise they couple very weakly to anything else, which is why we haven't observed them yet. Now, having said all of this, that it's to do with discovering, let's say, new forces, new matter, it is also possible, and that's why I said all of these directions are really exciting for someone interested in the foundations. It's also possible that it's to do with general relativity not being the ultimately good account of all of these phenomena. Maybe certain things change at certain distances, scales, and this has to be taken into account to modify the equations. And the interesting thing, and I think this is something we face all the time in physics, is that our final equations, both of general relativity and quantum mechanics, seem so beautifully mathematically coherent and tight that any modification we do spoils them in usually in ways that we don't want to really follow up. So it's really an intellectual challenge, even if it's true that it's not hidden energy that we haven't discovered, or hidden matter. If it's really to do with the theories, then we honestly don't know what to do. How do we modify them so that we keep all the other good features that we know are good, and not spoil them by the modification, and then account for these new phenomena? So I think all of these are possibilities. They are wide open. Certainly, if I was a um, young PhD students starting in physics, I would be jumping on questions of this kind, because I think they reveal to us the biggest amount of uncertainty we have in our knowledge, and therefore most likely places where a breakthrough will happen sooner or later.
In a similar fashion, one such other conundrums that we face or find when we study quantum mechanics is, well, the topic of entanglement and non-locality. Locality suggests is that any object faces any influence from a certain constructed environment, its immediate environment. However, what we
That's it.
see or observe with quantum entanglement, it even defies speed of light, because the exchange of information is instantaneous way. How are we currently tackling to answer this conundrum or to find a solution to this?
Yeah, so this is another a very good point, that to me what this shows is that if once you've observed entanglement, you really ruled out any description that's based on classical logic and classical algebra, as well, as I mentioned. So if you really think that the property you are trying to measure, like the position of your particle, or the speed, or the spin, or the energy, if you think that there is a real number that describes this, which means that the property is classically there, even independently of your measurement, then this is a mistake. That's actually what entanglement is telling us, that if you really think that things exist independently as classical numbers, independently of you measuring them and obtaining the results, then you are never going to be able to explain quantum entanglement. You will never get the correlations of the kind needed. And these are the famous Bell's inequalities. Bell wrote down inequalities in the early 60s, and he said, let me really try to model one quantum system with the classical real number algebra, take another system and I model it classically as well. And now I do measurements on them, and I try to see how much the outcomes to one observation could actually be correlated. When I measure the speed of this system to be 5 meters per second, what is the correlation with the speed of the other system? And Bell derived an inequality and said no classical description can exceed this number. And actually, our quantum experiments, and especially the Nobel Prize winning ones, were really done with high fidelity and are the best, if you like, violations of these Bell's inequalities that we have to date. Now, you could conclude one conclusion that you're drawing, and I think Bell himself was discussing this quite a lot. You could say, well, it doesn't necessarily rule out classical description. It could be that we have a classical description, but the price to pay then is what you said, that things happen instantaneously. So if I want to adhere to a classical description, then I really have to acknowledge that the only way they could be correlated is that something communicates instantaneously between these two systems. If you, on the other hand, and I think this is the alternative I would go for, and probably most physicists at present, if you want to preserve locality and causality of the kind that you don't want to allow anything to go faster than the speed of light, then the way you are forced to approach this is with these quantum numbers. You simply have to say, my systems, before I measure them, can only be described by these very weird objects, by these matrices, which obey a very weird algebra. But if I acknowledge that, then any interaction I have can be made local. It will propagate no faster than the speed of light. But now I'm really acknowledging that the underlying reality is much more complex, much more complicated than classically speaking. So it's a very interesting dichotomy. The choice there is if you abandon quantum numbers, if you abandon this quantum reality, then you automatically have to violate relativity. You have to say the only way I can account for experiments is to break the speed of light. However, if you want to keep the speed of light, then you are forced into acknowledging this quantum reality. And then you can save locality, but remember, locality is now not classical field locality, but really these quantum numbers that couple locally to one another, and you get a network of quantum numbers that become more and more entangled, if you like, in this language. And so that's the reality exactly that we are testing as we are growing the size of entangled systems. Can you really entangle everything ultimately? What kind of state would that be if many systems were entangled at the same time? It's a very different to anything we've seen in classical physics.
Very intriguing. You know, I might be traversing into a little sci-fi domain since this has been a little
Okay.
uh, plot point that has been utilized a lot. The concept or the notion of the multiverse or other worlds than
Yes.
our own. And from what I tried to research upon my own, there have actually been studies of formal research being conducted to sort of correlate the existence of this into reality. What are your thoughts upon?
Yeah. Yes, I think it's a good question because if you really think that quantum mechanics is all about um, entanglement expanding in a more and more complex network, but never collapsing, which is a bit like what Schrodinger had in mind with his famous Schrodinger's cat experiment, that you start with an atom that decays and doesn't decay at the same time. It emits something and doesn't emit it, exactly in a quantum superposition. And then Schrodinger says, oh, wait a second, whatever this couples to has got to join exactly the same superposition. It's always the same logic with quantum mechanics. So Schrodinger dramatized it by saying, what if I put a bottle with poison, and if when atom emits, the bottle is broken and the poison comes out? But there is the other possibility in quantum mechanics that it doesn't emit, and then everything is okay. The poison stays in the bottle. So somehow he said, I have these two realities in which the result of the simple quantum decay initially is a macroscopic event, death of a cat. We can all see whether the cat is dead or alive. And in the other branch, it's dead. However, quantum mechanics, if I take it seriously, and he was taking his own equation seriously in this case, Schrodinger's equation, it tells you that both happen. You must acknowledge these multiple realities. And that's exactly why some people like to use this many worlds, multiverse idea, that all of these possibilities, if the universe really is fully quantum, we don't know, it's a big if, but if the whole universe is subject to quantum mechanics, then I think that would be an appropriate picture. And it gets harder and harder to test, and this is an interesting point maybe that I should mention. It gets harder to test, um, not necessarily because something weird happens with quantum mechanics, but because having too much entanglement with everything else that you don't control results effectively in a classical description. So this is something that's not much appreciated either. By the way, not in physics either. There are many physicists who don't think about these things or don't think about quantum mechanics necessarily this way. But um, a classical Newtonian description only exists, if you like, because everything is hugely entangled. It's only because everything becomes hugely entangled that in each of these branches things seem to behave to a high approximation according to Newton's laws. So even classical physics owes its existence, if you like. I like to think of it that way because I think it's more fundamental to start with everything being quantum and then set up the conditions under which it would become classical. So you see the problem, let me put it in terms of technologies. The problem with our computers is not that our qubits are not good at entangling. They are actually too good at entangling. We'd like them to only entangle to each other, but not to anything else in the laboratory. We don't want them to entangle to light outside of our experiment, to other atoms that may be present, to the optical table, to other people, or anything like that. We'd like the computer to stay quantum within its own domain, but not to spread the quantumness everywhere else. Because once you entangle to everything, you effectively become macroscopically classical. That's the quantum road to classicality. So our problem, in fact, is to isolate these systems well enough. That tells you why putting a bacterium in a superposition is much more complex, because it's made up of lots of atoms and molecules. And all of these guys are simultaneously trying to quantum entangle to everything else. Much easier to isolate a single atom and to say, okay, I'm going to prepare it in this state. It's going to stay in that state for a long time. It's not going to couple to anything else. But as soon as you have many of these, you're just growing exponentially the possibilities for some entanglements to happen that you cannot control. So I think this picture is really what you called, I think it's appropriate to call this many worlds. It's just maybe two things to add to this. One is that the whole world then is still quantum mechanical according to this. So I want to discriminate this picture of many worlds from many other pictures that people are promoting, where they say, oh, maybe there are other universes with other laws of physics and so on. That's not the case here. The whole universe here obeys quantum mechanics. There's no problem there. But actually, within that description, you have multiple classical realities all somehow existing in an entangled state with one another. So that's, I think, important to understand. And the second point I like to emphasize usually is that this is a special case of the quantum state. You can have anything else in between. So in quantum mechanics, you can start with no entanglement between anything. You can then ramp it up a bit and say, oh, it's a little bit entangled, in which case you cannot talk about different worlds yet. And then as they become more and more and more entangled, the ultimate limit of that is to get many distinguishable classical worlds. So somehow this multiple universes reality is a special case as well. So I like to usually emphasize that quantum mechanics accounts for everything in between these two. So it's even more science fiction in your terminology than what people usually talk about. In fact, it's much weirder than just many worlds. It's everything in between, no worlds and many worlds simultaneously, if you see what I mean.
I'd like you to talk about consciousness as a subject from perspective of physics.
In fact, that's maybe the topic I certainly know about the least, but I think um, it's another topic that I usually mention when people ask me, and in fact, I'm in the process of finalizing a book on the topic of what are the five gates, if you like, five portals that it's really a metaphor for the experiments, if you like. These are the five experiments, or they are more like sets of experiments. Each of them is a number of experiments in the same direction that we could do to really probe for new physics. And I think consciousness seems to me um, another direction, simply because I already mentioned that people say gravity might collapse quantum mechanics, living systems might collapse quantum mechanics, and then there is a third view which says that it's all about conscious observers. That when a conscious observer observes something, this is tantamount to the collapse of the wave function, if you like, collapse of the superposition. It then definitively determines whether something is sitting on the left hand side or on the right. It can't be in a superposition any longer. And there are many physicists, actually many great physicists historically, who have held this view. Wigner probably is one of them, von Neumann another one. Currently, I guess Roger Penrose is possibly the most distinguished scientist that we know, who thinks that somehow consciousness will end quantum superposition. So to me, this is a fascinating topic because, of course, doing these kind of experiments with a human being, you know, instead of a cat, put a human being not with a poison. You know, you don't have to be cruel. You can put a human being to observe the outcome of a simple quantum measurement. Put a photon in two places, get a detector to click in one place or the other place, and have a person. And the reason why you want the person is precisely because we can communicate with humans faithfully, and we are testing conscious response. I mean, for all that we know, obviously, it could be that many other animal species are also conscious, and I'm not ruling that out, but I think it's difficult communicating definitively with them the same way that you are with a human. However, controlling human quantum mechanically at that level may well be an exceedingly difficult task, which is why I think what may happen before is that we have a good enough simulation, some kind of artificial intelligence, which is so. The interesting thing here is that it wouldn't be sufficient that this is classical artificial. All of these people developing now, first of all, it's not clear that this kind of intelligence is anything to do with human intelligence. There's a big question there. Probably not, actually. Probably we need to understand a lot more. But secondly, it's certainly not quantum mechanical. We should really be trying to develop a quantum computer and ask a question of how few quantum bits could we have and call this entity conscious. To me, that sounds like an amazing question. Can I have 1,000 quantum bits, only 1,000 quantum bits, and could this entity behave in a conscious way? What we humans would recognize, if you like, as conscious behavior. Once you have that, if you have that, you could, of course, experiment exactly in the way I was describing with other entities. And I think the key experiment there, maybe that's I can touch on that very briefly. I'm almost giving you the whole outline of my forthcoming book, which is great. I think it's a year to go, basic books, but it's kind of now in the production stages. I'm trying to put final touches and make it read better. But I think all the ideas are there, and the idea is the following: if this conscious entity, think of it as a human for the moment, just to make things simpler. Imagine, imagine in the lab there is a person who observes a photon and sees, hears a click or sees a computer screen saying the photon is now absorbed on the left hand side or on the right hand side. The question to test really is, once this has entered a conscious observer like us, could we still claim that there is this multiple reality that we were discussing before, quantum mechanically speaking? So, could we design a test? And the answer is yes. Otherwise, I think this wouldn't be exciting. Could we design a test in which we know that the person inside has seen a definitive outcome? There's a photon in one detector or the other. However, from the outside, we know that both of these realities exist, and we can actually test them, that they're in a superposition. So both of these observations, in fact, exist. Each of them feels as real as the other. The person seeing one detector click says, yeah, I'm definitely sure I know which detector clicked. The other person says, yes, I'm equally confident. And actually, you can then interfere these two possibilities quantum mechanically and show that they were, in fact, parallel quantum realities and they existed simultaneously. To me, this would be a mind-blowing experiment. I've actually talked with many neuroscientists because, as you know, neuroscience is approaching various questions about our perception already in a way that they're trying to measure it with the usual kind of physical, with fMRI, very similar physics techniques. Actually, all of them are developed in physics. However, I think they're still not sensitive enough, it seems to me, to be able to probe the quantum level, if there is a quantum level. Even that's a question there. For our consciousness, does it ever operate at the level that exists in superpositions of states? And to me, this sounds mind-blowing, but it's even more mind-blowing that there is a test, at least there is a thought experiment that we could do to really test whether a single observer could simultaneously, if you like. So you see, our language even fails here. Should I call these two different observers? Is it the same observer but in two parallel universes? All of this is possible. And in fact, the crux is really, are they staying in this entangled state? Can I manipulate them in that way? You can see why I'd rather have a quantum computer, because obviously we know that a quantum computer is designed to be able to hold superpositions, be entangled, and so on. But then, of course, we better make sure that the answers we are getting from these quantum computer are faithful. You want to know that when the computer says, yes, I've observed a definitive outcome, you want to know that this really corresponds to a definitive outcome. With people, we are kind of quite sure that this is the case. If someone is telling you, I've seen this, unless, of course, they are malicious and they're deliberately deceiving you, you know that this is the case. And so the question is, will our technology ever get, you can almost invert this and say that this could be a test of quantum artificial intelligence. If it cannot exist in multiple realities, it's not quantum intelligent at all. You see what I'm trying to say? So rather than even testing consciousness, you could say, I think this is a requirement for a quantum consciousness, that it should be able to exist in multiple realities. So I can see many, many interesting questions in this direction.
A breakthrough like that might be quite far as far as
I think so.
implementation is
I
concerned.
think so.
However, I thoroughly believe if whenever we achieve that level of discovery and breakthrough in science in general, that might be the pinnacle of what we might want to discover.
Yes. Yes, I can tell you one thing just along these lines, is that a colleague of mine, from Switzerland, Nicolas Gizan, he did a very interesting experiment a few years ago, where he was violating Bell's inequalities. So he was one of the people in the race to really close all the loopholes and demonstrate definitively that entanglement is real. And instead, he decided to do the following thing, which I thought was very creative. Instead of using photodetectors, instead of using artificially constructed detectors to detect photons and then show that they are correlated according to quantum entanglement, he used his own students as detectors. So he would generate entangled photons, and at each end there was a student who was looking directly. And by the way, humans can see single photons. This is almost like an indirect test that you can detect single photons. So every time he would get the students to detect whether they see a photon or not, and then he would look at the correlations between the observations of the students, and they violated Bell's inequalities. Students were good enough to actually violate, to show that there is quantum entanglement. So now this really begs the question, what happens? It's not a question that he could probe, and it's not a question that we know even how to begin to ask. But what happens when they made these observations? Is it really possible that the entanglement from the photons was somehow transferred onto their brains, if you like? It's a very complex process, of course. Even the eye detecting something is an extremely complex process. How this propagates down the nerves and what kind of interpretation the brain puts on top is largely not understood, I think. But to me, it sounds like, why isn't each part of this process ultimately a quantum mechanical process? And that really sounds amazing. It's almost like Schrodinger's cat. You're trying to take quantumness from a very tiny pair of systems and imprint them onto as complicated systems as human brains. So how do we understand that? What does this mean? And I think I'm hoping experiments go in this direction as well. It sounds amazing.
110%. It really is. Like when you really sit down and try to think about it, try to conceptualize whatever this is and how it works, well, it really starts makes you think about what could be.
Yes, absolutely. And I think that's where we need to be creative, because remember, our theories are extremely important to have, simply because they also guide us as to what kind of experiments we should be testing. If I didn't know quantum mechanics and the rules of quantum mechanics, it would never occur to me to do an experiment where I'm thinking that a photon is in two places at the same time. That doesn't make sense according to classical physics. A classical physicist would not be designing these kind of crazy experiments. So I think your theory, understanding how perception works at this level, is extremely important, because it guides you as to what you think could and couldn't be done, experimentally speaking. And I think this is wide open. I really expect a lot of surprises here.
I really have a lot more things that I might want to discuss with you about. However, it's already been you've already given a lot of your time, and I'm utterly grateful for it. And I'd like to
Thank you.
end this particular.
Thank
Yeah,
you.
yeah, please go on.
No, no, please, please, yes. I think, uh, like I said, I'm very happy to discuss these things. We can talk about it on a separate occasion. But you are right that probably, you don't want to saturate the topic as well. But I think there are many interesting things to talk, things to discover in the future as well.
And with that, I'd like to, the final ending note of this discussion, what is your advice for the upcoming generation of physicists?
Advice is really to go into the quantum physics in the complex domain. I would say look for the situation, take quantum mechanics out of its comfort zone. Don't just go in the directions where we understand things pretty well, and you're just doing incremental research and discovering one small thing, maybe one application. Go into these areas that are wide open, and the direction really is in the macroscopic direction, increasing complexity, increasing number of constituents. What happens there? Does it still hold quantum mechanics? So I would really jump on all of these topics, and even try to phrase meaningful questions before you translate them into an experimental question. I think it's really wide open. I I think physics will go into more into chemistry, more into biology, and it will give us a better understanding of other sciences as well. That's how I see the next, let's say, 2 to 3 decades of science is actually quantum mechanics leaving the microscopic domain, going into the macro domain, and making fundamental contributions to chemistry and biology. And this to me is extremely exciting.
Dr. Vlatko Vedral, it was an utter honor to have this conversation with you.
Thank you.
Absolutely phenomenal, lovely, and highly, highly thought-provoking.
Thanks
Thank
very
you
much.
so very much.
Thanks a lot. Pleasure.
Uh,